The first objective for lesson 27 is for us to be able to convert between logarithmic and exponential forms. In a previous lesson, we talked about what exponential functions are, and now that we know what exponential functions are, we can introduce logarithmic functions. Log base b of x is the same thing as the exponent that goes on the base of b in order to get x. So a logarithm is simply a fancy exponent. So every time you are trying to evaluate a logarithm, you are looking for the exponent that goes on the base in order to get whatever is on the inside of the logarithm. So for example, log base 4 of 16 is equal to 2 because 2, the answer for the logarithm, is the exponent that went on the base of 4 in order to get what was inside the logarithm of 16. Similarly, in number 2, log base 5 of 0.2 is equal to -1 because -1 is the exponent that goes on the base of 5 in order to get what was on the inside of the logarithm. And note that 0.2 is the same thing as 1/5. In number 3, log base 8 of 1 is equal to 0 because this is asking us to find the exponent that goes on the base of 8 to give us 1. Number 3 is very similar to number 4 because log base 23 of 1 is also equal to 0 because 0 is the exponent that goes on the base of 23 in order to give us 1. So notice that for every logarithmic equation, we were able to write an equivalent exponential equation. Being able to switch back and forth between logarithmic and exponential equations is going to be fundamental to this entire lesson. Switching back and forth between those two is realizing that these two equations are in fact equivalent. The same way that we were able to start with a logarithmic equation and write an equivalent exponential equation, we should also be able to start with an exponential equation and write an equivalent logarithmic equation. So because 2 to the 4th is equal to 16, that means that 4 is the exponent. 4 is the exponent, and the exponent is equal to the logarithm. Now, which logarithm? It's the log with a base of 2, and 16 was inputted into it. So every time we're looking at this exponential equation, we need to grab the exponent and say that the exponent is what the logarithm is. Now, which logarithm is it? It's the log with a base of 27 that 3 was put into. Similarly, in example 7, if the exponent in this equation is -2, that means that -2 is the exponent that went on the base of 1/4, which will be the same base of the logarithm, in order to give us 16. So far we have covered our first objective. We have started with logarithmic equations and switched them to exponential equations. And similarly, we have also started with exponential equations and then switched those exponential equations to a logarithmic equation. So we're able to switch back and forth because we know that these two equations are equivalent to each other. They're just saying the same thing in different ways. Now that we know what a logarithm is, we should be able to evaluate logarithms. So that means that we should be able to look at example 8 and say log base 12 of 144 means what exponent goes on 12 to get 144. So we are looking for what exponent we put on 12 to get 144, and we know that that exponent is 2. So log base 12 of 144 is equal to 2 because 12 squared is equal to 144. So remember, in all of these problems, we are looking for the exponent. So in number 9, we are looking for the exponent that goes on the base of 64 to get 8. It might be tempting to say 2, but remember, it is 8 squared that is equal to 64. But we don't have a base of 8. We have a base of 64, and the exponent that goes on 64 to get 8 is 1/2, because 64 to the 1/2 power is the same thing as the square root of 64, which we do know is 8. So log base 64 of 8 is equal to 1/2, because when you take the exponent of 1/2 and put it on 64, you get 8. In example 10, we are looking for what exponent goes on 3 to give us 1 over 27. This might be a little bit tricky, but we have to think about rules of exponents. We know that 3 to the third is equal to 27, which implies that if we had 3 to the negative 3, we would get a 1 over 27, because negative exponents send things to the denominator. So log base 3 of 1 over 27 is equal to negative 3, because 3 to the negative 3 is equal to 1 over 27. Notice that in all of these examples, we were able to evaluate a logarithmic expression by giving an exponential equation to justify our answer. All of these logarithms that we got answers for, we were able to write some equation with an exponent in it to justify that answer. We're going to continue to look at examples where we use exponential equations to evaluate logarithms, but there are 2 new logarithms that we have to introduce. So far, every logarithm that we have looked at has explicitly had a base written on it. In example 11, we can see that our logarithm does not have a base written on it, and when that is happening, when we see log written with no base, that is the same thing as log with a base of 10. So when we look at example 11, we have to be able to understand that this is the same thing as log base 10 of 100. And then the question becomes, what exponent would I put on 10 in order to get 100? And that exponent is 2, and the logarithm is the exponent. Similarly, in example 12, we have to realize that this is the same thing as log base 10 of 0.0001. So what exponent goes on 10 in order to get 0.0001, and that 0.0001, and that exponent is -4. And so the logarithm is equal to -4. So notice in both examples 11 and 12, we were able to evaluate a logarithm by using an exponential equation to justify our answer. So every time we write the answer for a logarithm, it is because whatever that answer was the exponent that we were looking for. Examples 13 and 14 are a little bit different because we do not see log written out, we see ln. ln stands for natural log. ln stands for natural log, and it is the logarithmic function with the base of e. E is an irrational number, and it is the base of the natural log function. So in example 13, natural log of e to the -3 is the same thing as log base e of e to the -3. So that is asking us what exponent, what we're looking for, is what is the exponent that goes on the base of e. We have to understand that natural log has a base of e in order for us to get e to the -3. And that exponent is -3. In example 14, natural log of e to the 10th is asking us what is log base e of e to the 10th, because natural log and log base e are the exact same thing. So we are looking for what exponent. A logarithm is an exponent, and it is specifically the exponent that went on the base of e, and the base is e because natural log has a base of e, in order for us to get e to the 10th. And that exponent would have to be 10. In examples 15 through 18, we're being asked to use our calculator to find these approximate values, and we want to round to 4 decimal places. So a quick example here. If on your calculator you type in log of 43, your calculator will return about 1.6335. So what your calculator is telling you is that when you typed in log of 43, that meant that you were looking for what exponent went on the base, and log written with no base is the same thing as log base 10. So this is you asking your calculator what exponent goes on the base of 10 in order to get 43. And then your calculator is telling you that that exponent should be 1.6335. If you check that in the calculator, when you do put that exponent on 10, you do approximately get 43. And so that is what we will be doing. These are not logarithms that could be evaluated exactly, like how we had in examples 11 through 14 and how we had in examples 8 through 10. These we were able to evaluate exactly because we can find nice integer or rational exponents that go on these bases to give us what's on the inside of the logarithm. But for an example 15, we cannot find a whole number that is the exponent that would go on 10 in order to get 200. So instead, we just go to the calculator and we type in log 200 in the calculator, and the calculator gives us approximately 2.3010. And then we can check that in the calculator, because when we take this exponent and we put it on 10, what we get out is something that is very close to 200. We get out 199.986. Example 16, I'm evaluating log of 0.074 in my calculator. This gives me approximately negative 1.1308. And what that means is that if I were to take the exponent of negative 1.1308 and put it on 10, what we would get out would be something that is very close to 0.074. And I get out 0.073994. Example 17 is natural log of 200. This is asking us to find the exponent. What we are looking for here is what is the exponent that would go on the base of e, because the natural log function is the same thing as log base e in order to give us 200. That's nothing that we could think of by ourselves, so in the calculator we type in natural log of 200 and the calculator gives us approximately 5.2983, and that is because if we were to take the exponent of 5.2983 and put it on e, what we would get out would not quite be 200, but it'd be very close. This is an approximation. We get out 199.9965. And then finally, natural log of 1.005. The calculator returns approximately 0.0050, and that is because if you were to take e and put the exponent of 0.005 on it, what you would get back out would be about 1.00501. So some logarithms we will simply evaluate or approximate by just typing them into the calculator and getting their approximations back. Our third objective for this lesson is for us to be able to apply basic properties of logarithms. There's 4 properties that are listed here. Rather than going over them abstractly, let's look at these examples and remember to keep in mind that a logarithm is simply an exponent, and we're going to use that to evaluate these. So in number 19, we are looking for log base 19 of 19. Whatever the answer to that is what the exponent is that goes on 19 in order to get 19. But the exponent that goes on 19 to get 19 is 1. And so log base 19 of 19 is equal to 1. In example 20, we have log of 10. We have to know that log is the same thing as log base 10 of 10. So this is asking us to find the exponent that goes on the base of 10 in order to be equal to the 10 that was plugged on to the inside of the logarithm. And that exponent has to be 1. So what 19 and 20 illustrate is the same thing that 21 is going to illustrate. Let's go ahead and work out 21. Natural log of e is the same thing as log base e of e, because we have to recognize that natural log and log base e are the same thing. So what this is asking us to find is what is the exponent that goes on e in order to get e, and that exponent is 1. So what we see in examples 19, 20, and 21 is that when the base matches what's on the inside of the logarithm, the logarithm evaluates to 1. That's the same thing that happened in example 20, because the base and the inside of the logarithm were both 10, and that's the same thing that happened in example 21. The base and what was on the inside of the logarithm were equal. So in all cases, the exponent that we ended up putting on the base was simply 1. And that is one of our properties of logarithms. Is the second property that's listed here, that when the base and the inside of the logarithm are equal, the logarithm is equal to 1, because b to the 1 is equal to b. Now we're going to look at examples 22 and 23. Notice that in both examples 22 and 23, we simply have a 1 on the inside of the logarithm. So in both of those examples, we are looking for the exponent that goes on the base. In example 22, the base is 273, and we want this to come out to be 1. So what exponent do we put on 273 in order to get 1? Well, that exponent is 0. Because anything with an exponent of 0 on it is equal to 1. And once we have found the exponent, then we have found the answer for the logarithm, because the logarithm is simply an exponent. So in number 23, I'm looking for what exponent goes on the base of 1/8 in order to give me the 1 that's on the inside of the logarithm. And again, that exponent is equal to 0, because anything raised to the 0 power is equal to 1. Because anything raised to the 0 power will give us 1, that means anytime we have 1 on the inside of the logarithm will be equal to 0. Because if 1 is what's on the inside of the logarithm, that's what you're trying to get your answer for the exponential equation to be, and that means that the exponent was 0. Example 24, we have log base 30 of 30 to the 10th. Remember, a logarithm is simply an exponent. In particular, we're being asked to find the exponent that goes on the base of 30 in order to give us what is on the inside of the logarithm, which is 30 to the 10th. And that exponent we can see is 10. And this is an illustration of the third property that we have here. So when the base of the logarithm matches the base of what's on the inside of the logarithm, they cancel out and leave you with whatever the exponent was. Something similar is going to happen in example 25, because remember that natural log is the same thing as log base e. So this is log base e of e to the negative 12. So to evaluate this, we're looking for what exponent goes on the base of e in order to give us e to the negative 12, and that exponent is e to the negative 12. Number 26 and number 27 are a little bit different. To evaluate these, let's think about what we have going on in the exponent. In the exponent here, we have log of 14. But we have learned that log of 14 represents the exponent that goes on 10 to get 14. So if log base 14 is the exponent that goes on 10 to get 14, and we have now made it the exponent of 10, then this is simply equal to 14. In other words, it's saying that 10 to the log base 10 of 14, that the log base 10 and the 10 itself will cancel out and simply leave us with 14 as the answer. And that makes sense for them to cancel out, because exponentials and logarithms are inverses of each other, and inverses cancel each other out. Similarly, in example 27, we know that log base 8 of 5 is the exponent that goes on 8 to get 5. And it is written as the exponent on 8, and so this is equal to 5. And both examples 26 and 27 are illustrations of this final property of logarithms. In example 28, we're being asked to graph exponential functions, and we are going to do that by first rewriting it in exponential form, and then we'll be plugging in values for y. Remember that a logarithm is simply an exponent. So if log base 3 of x is equal to y, that means that y was the exponent that went on the base of 3 in order to get x. So now we have an equation 3 to the y is equal to x, for which we can plug in values for y and get out values for x. So I'm going to choose some values for y. Now that I've chosen some values for y, I'm going to be plugging them into this equation in order to get x. So for example, when y is negative 2, x would be 3 to the negative 2, which is 1/9. When y is negative 1, x would be 3 to the negative 1, which is 1/3. I'm taking these y values and I'm plugging them in as the exponent of 3. And now I have some points on this graph that we can plot. And this is what the graph of log base 3 of x looks like. Example 29, we're going to do the same thing. We're going to convert this logarithmic equation to an exponential equation, and then we're going to plot some points and graph. But first, we need to isolate the logarithm in the equation. So I'm first going to subtract 2 from both sides of this equation to get that y minus 2 is equal to log base 2 of 1 plus x. And we know that a logarithm is simply an exponent. So if this logarithm is equal to y plus 2, that means that if this logarithm is equal to y minus 2, that means that y minus 2 was the exponent that went on the base of 2 in order to get 1 plus x. And now to make this equation easier for us to work with, I'm going to subtract 1 from both sides so that I can solve for x. We get that x is equal to 2 to the y minus 2 minus 1. And now we can use this equation to again plug in values for y and get out values for x. So what I'm doing is I'm choosing y values. Say I choose the y value of 2, and I'm going to take this y value of 2 and I'm going to plug it in right there. So I would have 2 to the 2 minus 2 minus 1, which is 1 minus 1, which gives me out 0. And I'm doing this so I can continue to fill out this table and get some points that we can plot. And now I'm going to plot these points. Before I connect these points, we need to think about what the domain of this logarithmic function is. In order to find the domain for a logarithmic function, we have to make sure that what's being plugged on the inside of the logarithmic function is greater than 0. So here I can see that the domain for this function is -1 to infinity. This function has a vertical asymptote along the vertical line of x is equal to -1. So when I go in to connect these points, I want to make sure that we're not touching or crossing that vertical asymptote and that we're simply getting very close to it, because the domain of this function is -1 to infinity. Down here we have a review of transformations that can help us with graphing logarithmic functions. Another thing we could have noticed up here is that the +1 on the inside of the function is going to take the graph to the left 1, which is why the vertical asymptote is at x is equal to -1. At the top of this last page, we have a quick review of putting together exponential functions and logarithmic functions. Remember that these functions are inverses of each other, so their graphs are reflections of each other over the line y is equal to x. That also means that the domains and the ranges of these functions will switch. One function's domain will be the other function's range, and vice versa. Exponential functions have horizontal asymptotes, while logarithmic functions have vertical asymptotes. The last set of examples we're going to look at are us finding the domain and range and the vertical asymptote for these logarithmic functions. In example 30, we can look at this graph and see that this function has been pushed to the left 3, meaning it has a VA at x is equal to -3. We can find the VA by setting the inside of the logarithm equal to 0. The domain of this function is all real numbers that are greater than -3. We can see that by making sure that the inside of the logarithm is positive, greater than 0. And the range of this and any other logarithmic function is all real numbers. In example 31, the vertical asymptote of this logarithmic function is x is equal to 0, because this function was not shifted to the left or the right. The domain of this function is from 0 to infinity, and the range of this function is all real numbers. We can see that the domain is from 0 to infinity by making sure that what's on the inside of the logarithm, which is x, is always positive, greater than 0. In example 32, we now have a quadratic on the inside of the logarithm. In order to find the domain of this, we want to make sure that what's on the inside of the logarithm is greater than 0. So we're looking for where this quadratic is positive. If we were looking for the vertical asymptotes, we'd be looking for where this quadratic is equal to 0. Now, in order to solve this inequality, we have to first solve this equation, which can be solved by factoring. This factors into x minus 4x plus 1 to give us two answers of 4 and negative 1. That lets us know that the x-intercepts for this quadratic function are negative 1, 0 and positive 4, 0. So that the parabola looks like this. We are trying to solve when is this parabola greater than 0? When is it above the x-axis? Well, it's above the x-axis on two separate intervals from negative infinity to negative 1, which makes sense because we can see that we do have a piece of the graph to the left of this VA, which must be at x is equal to negative 1, and it's also above the graph from 4 to positive infinity. So this is our answer for the domain. And that makes sense because we can see we have a second vertical asymptote here at what must be x is equal to 4. So we have two VAs, and there is our domain, and the range of this logarithmic function and any other is all real numbers.